So how do you go from this particular example? Because to my mind anyway, this seems like the most bizarrely difficult thing to break out into a series of cosine. So here's our function, and I'll call it x of t. So Jonathan, I'm going to tell you right now, just intuitively, that you break this into a series of cosines, just kind of by inspection. And each one is the one that fits this waveform the best. So this would be the first one. And out of curiosity, Jonathan, what would you say the magnitude of that is? Let's say that the thing you're trying to find is a +1 to -1 waveform. And this is at a quarter. This is a half. This is at 3/4. Kind of hard to see. This is at 1. This is, so it's got a period of 1. What would you say the amplitude is of that green best fit cosine wave?
That'd be 2 volts peak to peak.
You'd guess 2 volts. Okay. You'd guess that would look like 2. That's not what I've drawn. If I drew it as as that, it would probably look more like, let's see, 2. That would look like more like, that would be about 2. Does that look to you like it fits it the best?
Oh, I was saying like peak to peak, so like the bottom all the way to the top.
So in that case, you'd say,
So it'd be like a total of 1 up and 1 down.
so if it's trying to fit a red thing of 1, then you can see that going up 1 and down 1 puts you in here. Now you can already see that that's not the best because that always underestimates it and it never overestimates it. So that's not the best fit. Do you see why this always underestimates it and never overestimates it? Do you see that, Jonathan?
Oh, yes, sir.
So give me an updated guess now of what you would guess the best fit cosine wave would be for that. Some of the time overestimates it, some of the time underestimates it, so that this area here where you underestimate it is equal to this area here where you overestimate it.
Probably like 1.5 then.
Okay. So your best guess is 1.5. And what I want to do at the end is just go back and see how close your intuition is based upon what we said. And you can actually see, you can continue on with this. You've overestimated in certain spots and you've underestimated in other spots. And there's no way around that, right? So our second guess for a cosine wave, we've overestimated here. So we want it to go underneath in that region to try to bring it back. And in this region, we've gone too far. We want to bring it back. We want to bring it back. So we want the next cosine waveform to look like this in these regions. But our original square wave goes straight up and down. It instantly goes up here. So no matter what it is, we know we want it to go, has to have a positive slope here. And by the same reasoning, if it goes infinitely down, it better have a negative slope here. And then hopefully as we add up these 2 positive slopes and these 2 negative slopes, it'll make something that's got even more of a positive or negative slope, and it will approach our infinite slope. So our next one you can see would look something like, would have to look something like this. It's a little bit messy, right? And we're not getting it all perfect. This would have to be like that, so it'd go like this. Okay. And there's something interesting to notice here is that if we have this frequency of our first, if this frequency is 1, this is the same frequency as our underlying red form that we're trying to duplicate, red waveform. Our first guess of our cosine wave has the same frequency as the frequency of periodic waveform. And then our second waveform here, in the same period, it has 1, 2, 3. It's an integer multiple. This particular one happens to be 3. You might have some that has 2 for your second waveform that goes into it. But if you think about it, it's always going to be integer multiples of your fundamental frequency, because if your fundamental frequency part repeats every period, then the parts that make it up of the cosines all better also repeat at that lowest possible frequency. That's a difficult thing to state. Does everyone understand what I'm saying when I say that? Does anyone not understand the idea behind it?
Could you repeat that just real quick, saying it a little differently?
I'll write it down. From an intuitive standpoint, from this diagram, if our x of t that we want to duplicate, that's the thing that looks our square wave here, has a time period of t, then our first cosine, which we call our fundamental, and sometimes we also call it our first harmonic, it also has a period of t. And that should make sense if you're trying to duplicate something that is periodic in t. Your cosines would all, your biggest part would probably have a period of t. But also, all higher frequency, also called all higher harmonics, all these other cosines that make up your x of t will all have integer multiple frequencies of t. In other words, you might have a harmonic waveform that is twice the fundamental period, or 3 times or 4 times or 5 times, but you'll never have one that's the square root of 2 times the fundamental. Because if it was the square root of 2 times the fundamental, then after one period here of your underlying waveform, the thing that you're trying to build your waveform by, that cosine, hasn't repeated. And so that would be a bad choice to build your x of t. Does that make sense? It's difficult.
Yes, that makes sense.
Thanks. It's difficult to say in words, but I think it's clear when you see the picture. And when you understand what the intuition is, it's a whole lot easier seeing the math behind it. If you can get the intuition behind this down, then the math is actually a whole lot easier. All right, here's an example of a time domain waveform. And I want to show you what the fundamental best fit waveform is to make it. And it's this thing in red. And it turns out that there is no, and this is at the same frequency. So if this underlying blue thing had a frequency of 1, red has a frequency of 1. Turns out that there's nothing that has a frequency of 2, because if it had a frequency of 2, it wouldn't go down here and up here, but also do the opposite thing where it overshot. Instead, instead there is a third harmonic. And you can see how this third harmonic always goes in the correct direction of our underlying blue. When blue goes up, this magenta goes up too, but it always goes in the opposite direction of where our fundamental reconstructed waveform overshoots or undershoots. And if we were to add those two together, it would look like this. You get what it's trying to do. Now, if we add in another waveform, another harmonic, there's nothing at 4 times the fundamental frequency for this particular waveform, but there is at 5. And this 5 helps, remember when we added the 2, it still had this thing over negatively corrected. So now this thing compensates for that, but it still is going in the direction of our underlying blues instantaneous changes. And when we add that up, we get something that looks like this. So again, this was our first. We added another one, we got closer, we added another one, we get closer. And as we continue to add them, we get something that more and more closely approximates a square wave, even though once we get, these are all of them added together and they just look like mush, don't they? But when you add them up together, it looks arbitrarily close. And this is with 38. So here's with 40. And what Fourier said was in the limit, it perfectly exactly matches as the sum goes to infinity. And not only does the sum go to infinity, But look at the nth sine wave as we do this. As we get higher and higher frequencies, there's less and less magnitude required for it. So in the limit, the size of the sine wave also goes to 0. Let me give one other example of where we're headed with all this. So you can see as you get other kind of waveforms, like here's a triangle waveform. This already looks kind of like a sine wave. So therefore, it doesn't take many harmonics. After 7 waveforms, after 7 harmonics, it's a really close approximation to it. If we screw around to the symmetry, though, if we make it look something with these sudden changes, this is really hard to model with a sum of sine waves. So this takes quite a few before it gets to be a close approximation. But I represent you that it will still work no matter what kind of waveform you have. We can even do weird things of sine waveforms. Now, since the sine waveform is a distorted sine, it doesn't take many sums at all before you get a really close approximation to this. After maybe just 13, it looks almost identical. Just to gather a little bit more intuition behind this, Charles, if we delay this underlying waveform, if we delay our blue waveform left and right, how will that affect the sum of the Fourier components?
Well, you need to do something to delay those as well.
That's it. The magnitudes stay the same, and they just change in phase offset. So if we were to sum them all up, let's get a few. Whoops. Let's sum them all up. If you delay the underlying waveform, you're just delaying the magnitudes. I'm showing you here's the magnitude terms that I'm graphing here. This is the first one. This is the second one, the third one. The magnitudes stay the same. But if I show you the phase of them, as I delay my waveform back and forth, the phase of all of them change around quite a bit. Let's go back to the magnitude terms. Don, can you tell me, as I change the amplitude of my underlying waveform, as I change this amplitude bigger back and forth, how will that change the magnitudes of the sine and cosine waves that reconstruct it?
So your first wave is going to have to match that amplitude, and all the subsequent waves are going to have to go in with that.
Right, exactly. So as we increase the blue, we increase the red too. And in fact, all of them, if we increase the amplitude by a factor of 2, we just increase the magnitude of all of their component waveforms by a factor of 2. Phil, how about with frequency? As I change the frequency of my underlying waveform here, how is that going to change the magnitudes of the cosines that reconstruct it?
So it's going to change them with the frequency that you're changing it. So since it's you said they're all like a multiple of a real number, it's going to just, affect it the same way.
That's it. So what happened? The frequencies of the underlying ones will be affected the same way, but what will happen to their magnitudes? Remember, a cosine is defined by 3 numbers. Its frequency, its magnitude, and its phase. As we change the amplitude, as we change the amplitude of x of t, we likewise change the amplitude of all of its component cosines. As we change its frequency, what do we change?
You're just changing the frequency.
Yeah, and so exactly, and so the magnitudes stay the same, and you can see this as we show that construction again. I'll show them all, show a few of them, and as we change the frequency, it changes the frequency on this line, but the magnitudes don't change one bit. Symmetry obviously changes your construction, and if we had a perfect symmetry, if we have a perfect symmetry of 0, then in fact there's only one. No matter how many components I give you, it really only needs the fundamental, and it's complete. This is an example of a single phasor. And we represent this phasor as a point on the z-plane, right? So this particular point is up here, and you can see what this phasor does by allowing it to rotate around at its frequency. And if you project the head of this phasor on this real line, then how far it is in the x direction, left or right, this black dot corresponds to the vertical position over here. So when it's all the way to the right, So when it's all the way to the right, I can't stop it. When it's all the way on the left, it's at the bottom. When it's all the way at the right, it's at the top. So now what happens if we want to model a square wave? And I'll put in the second harmonic there. Now we've got these two phasors. And remember how I said that they're at integer multiples? So this second one, smaller one, is rotating at 3 times, exactly 3 times the speed of the first. You can see that they'll always line up exactly over this vertical thing. Boom, they've lined up perfectly. But when you add the two together, vector addition works, and the projection of the end of their sum goes back and forth, and you can see it hangs out on the right for a little bit, it hangs on the left for a little bit, it hangs out up here a little bit, it hangs out down here a little bit. If we were to add another component to it, now we've got 3, and now it's a pretty good approximation. And we could continue to do that with more and more components of the Fourier series. So now you're seeing in the phasor domain what the sum of 3 Fourier components does and how closely it corresponds to your overall square wave, which is one of the hardest ones to do. Here's another hard one. Here's a sawtooth wave. So here we've got 5 different harmonics, and you can see how it slowly moves to the right and then quickly unfurls to the left. It's even possible to create an impulse train with it. Here's the first 5 components that make an impulse train. Stays close to the 0 and swings out to the right. Stays close to the center and swings out to the right. So this is intuitively what Fourier is doing.